Good afternoon, students. Welcome to the 35th lecture of refrigeration and air conditioning subject. Today we are on the topic ammonia hydrogen refrigeration and problems, and also we are having the maximum coefficient of performance for absorption refrigeration system, and we are dealing other topics also. Right? We'll go into the class. So in the last class we have stopped the topic at that domestic Electrolux refrigerator. The ammonia hydrogen refrigerator is also known as a domestic Electrolux refrigerator. So this type of refrigerator was invented in 1925 while they are studying for their undergraduate course of Royal Institute of Technology, Stockholm. So here the idea was first developed by the electronics company of Luton, England. See here the domestic electronics type of refrigerator where the gas burner is burning the solution, thereby this solution is going into the rectifier and it rectifies under the ammonia vapors. Ammonia vapors are coming out and it is forming the form of condenser. From the condenser it is going into the evaporator, right? The liquid ammonia is going into the evaporator and it is going into this absorber. So here we are having absorber, whereas in the vapor compression system we are having compressor, right? So here this absorber will take this ammonia, liquid ammonia and hydrogen, and it is for converting the strong solution by passing into the heat exchanger. And in this heat exchanger the weaker solution is going back into this chamber and the strong solution is going into this chamber, right? So in this way the Electrolux or ammonia hydrogen refrigerator will operate. See here, this type of refrigerator is also called three fluid absorption system. So finally we are having two other names for this ammonia hydrogen refrigerator. The first one is Electrolux. Okay, the first one is a domestic Electrolux refrigerator or three fluid absorption refrigerator. The main purpose of this system is to eliminate the pump so that in the absence of the pump of the moving part, the machine becomes noiseless. So when we remove the pump, automatically the machine becomes noiseless. Therefore, this machine is a noiseless machine. The three fluids which are used in this system are ammonia, hydrogen, and water. So that's why the name given as ammonia, hydrogen, and water. So that's why the name is given as three fluid system, that is ammonia, hydrogen, and water. The ammonia used as a refrigerant because it possesses most desirable properties. Next, it is toxic in nature, but due to the absence of moving parts, there is a little chance for the leakage and the total amount of refrigerator used is very small. The hydrogen, being lightest gas, is used to increase the rate of evaporation, right? Rate of evaporation. Next, of the liquid ammonia passing through the evaporator. Fourth point, the hydrogen, the third fluid. The third fluid, the hydrogen is also, the ammonia, the hydrogen is also non-corrosive in nature and insoluble in water. This is used in low pressure side of the system. So the third one, the third fluid is the water, which is used to as a solvent because it has ability to absorb ammonia readily. Therefore, the principle of operation of the domestic Electrolux type refrigerator is shown in the figure 7.5 described below. So if you see the real-time physical absorption machine is this one. So the name is given as Electrolux refrigerator, or we are calling them as another name, Electrolux. Three fluid Electrolux or vapor absorption refrigeration system, right? So ammonia, hydrogen, and ammonia, hydrogen, and water. So why ammonia is used? Ammonia, the hydrogen is being in the highest. So the ammonia is used because it possesses the most desirable properties, which is toxic in nature, very light, and chances of leakage. Next, the hydrogen is non-corrosive in nature and is insoluble in water. That's why hydrogen is also used. Next, the water is used as solvent because it has ability to absorb the ammonia readily. The principle of operation is shown in the figure. The strong ammonia solution from the absorber through heat exchanger is heated in the generator, right? So what is saying here? From the observer, it is taken into the from the observer it is taken to the heat exchanger where you are given as observer, which you are taken that things. Next, applying from the heat of the external source during the usually by a gas burner. During this process, the ammonia vapors are removed from the solution and passes into the condenser. A rectifier or a water separator fitted before the condenser removes the water vapor carried with the ammonia vapors. So what does it do here at this point? So here from this point, so check from this point. Okay, so here if you take the ammonia, so if you take from this point, the liquid ammonia is going into this heat exchanger and going into the gas burner. Here it is converted into the vapor form, so it is passing into the condenser through the rectifier. That is this point what they have written. So during the heating process, the ammonia vapors are removed from the solution and passing to the condenser. Receiver is placed at that point, or water separator filters before the condenser to remove. Right? Next, rectifier or a water separator fitted to the condenser removes the water vapor carried with the ammonia vapors so that the dry ammonia vapors are supplied to the condenser. Now, the water vapors, if they are not removed, will enter into the evaporator, causing the freezing and choking of the machine. The hot weak solution left behind the generator flows to the absorber through the heat exchanger. Now, this hot weak solution while passing through the exchanger is cooled. Now, heat is removed by the weak solution is utilized in raising the temperature of strong solution passing through the heat exchanger. So that's why the absorption is accelerated and the improvement in the performance of the plant is achieved. Now, the ammonia vapors, which is in the condenser, as shown in the figure, the ammonia vapors, which is in the condenser, as shown in the figure, are condensed by external cooling surface. The liquid refrigerant leaving the condenser flows gravity to the evaporator, where it may right. The hot weak solution left behind the generator flows to the absorber through the heat exchanger. This hot weak solution, while passing through the exchanger, is cooled. The heat removed by the weak solution is utilized in raising the temperature of strongest solution passing through the heat exchanger. So like this, the absorption is accelerated and the improvement of performance of the plant is achieved. Now what does now from the condenser, the ammonia vapors are condensed by the external cooling surface. Therefore, the liquid refrigerant leaving the condenser flows under the gravity to the evaporator where it meets the hydrogen gas. Next, the hydrogen gas which is being fed to the evaporator permits the liquid ammonia. So liquid ammonia to evaporate at a low pressure and temperature according to the Dalton's principle. So during this process of evaporation, The ammonia absorbs the heat from the refrigerator shape and thus produces the cooling effect. That is the operation of this surface. Now, the mixture of ammonia vapor and hydrogen is passed to the absorber where ammonia is absorbed in water while hydrogen rises up to the water top and the flows out evaporator. The evaporator, therefore, the coefficient of performance of a filter is given by coefficient of expo F coefficient of performance is equals to heat absorbed in the evaporator divided by heat supplied in the generator. So like this you have to find out the coefficient of performance. Now based on this we'll do a problem. Now see, the total pressure maintained in an electronics refrigerator is 1.14.71 bar. The temperature obtained in the evaporator is minus 15 degrees centigrade. The quantities of heat supplied in the generator are 418.7 to disclose 1 kg of vapor and 1465.4 kg kilojoules per kg for increasing the total enthalpy of NH3. The enthalpy of NH3 entering the evaporator is 335 kg kilojoules per kg. Now taking the following properties of NH3 at minus 15 degrees centigrade, the pressure is 2.45 bar. The enthalpy H of NH3 vapor is equals to 1666. The specific value Vs is equal to 0.5 meter cube per kg. The hydrogen enters the evaporator at 25 degrees centigrade. The gas constant for H2 is equals to 4.2. For H2 is equal to 12.77 kg per kilogram. Now find out the coefficient of performance of the system assuming the NH3 leaves the evaporator at saturated condition. Right? So we have to find the solution. Now see the solution according to the question. The given PT, the pressure is equal to 14.71 bar. Temperature is minus 15 degrees centigrade. So 15 plus 275, that is 258. QG1418 and QG21465. For NH3, H1 is equal to 335 for P2 is equal to 2.45 bar. HT is equal to 1666. V is equals to Vs is equal to 0.5. And for H2, T3, 298 and R is equals to 4.2. CP is equals to 12.77. The schematic diagram of electrolux refrigerator shown in the figure 1.5. Consider the 1 kg of NH3 heat given to the generator. Qg is equals to Qg1 plus Qg2. Adding, we are having Qg1 and Qg2. Therefore, the value is this one. Since the evaporator PT is equals to 14.71 bar, P2 is equals to pH NH3 that is equal to 2.45 bar. Therefore, the pressure of hydrogen H2, that is pH2 is equal to PT minus P2, that is 14.74 minus 2.45, that is the value. Now refer the figure 7.6 for NH3 is equals to H1 is equals to 335 kg per kg. H2 is equals to 1666 kg per kilojoules per kg. Let M is equals to let M of H2 flows through the evaporator per kg of NH3. The ammonia NH3 occupies V is equals to 0.5 meter cube per kg, which is in the question. The value of H2 is equal to minus 2 degrees. So they have similar mentalities. So therefore the temperature is equals to 258 Kelvin. Now taking mass is equals to pH2 V divided by RT. So you are having the values pH2 value into V value into R value into T value. So this is the value you are getting. Now at the evaporator point, so at the figure, at this evaporator point, what happened? 1 NH3 kg you are releasing. Here the H2 is going. Here H3 plus hydrogen plus H2 as we want, right? So therefore, considering the energy balance for the evaporator, 1 of H2 minus H1, that is equal to Cp into M T3 minus T2 plus QE. Therefore, 1 of 1666 minus 335 H2 H1 is equals to 12.77 into M into T3 minus T2 into plus QE. So substituting the values, 280 here plus QE itself వచ్చేస్తే value, this is the value. Therefore, COP is equals to QE by QG, that is equal to 10431 divided by 1884.41, that is equal to 0.5536. That is a value. Now we'll discuss about the other type of refrigeration system in the absorption system, that is lithium bromide absorption refrigeration system. So what is the other one? Lithium bromide absorption refrigeration system. Now we'll see the next category. The lithium bromide absorption refrigeration system uses a solution of lithium bromide in the water. Here in this system, the water is being used as a refrigerant. So in the lithium bromide absorption system, it uses the solution of lithium bromide in the water. Okay, so water, what we are using lithium bromide as a refrigerant in the system. Here the water is being used as a refrigerant, whereas lithium bromide, which is highly hydroscopic in salt, as an absorbent. The lithium bromide solution has strong affinity for water vapor because of its very low vapor pressure. Since lithium bromide solution is corrosive in nature, the inhibitors should add in order to protect the metal parts of the system against the corrosion. The lithium chromate is often used as a corrosion inhibitor. This system is very popular for air conditioning, in which low refrigeration temperatures are required. So that is the concept of lithium bromide absorption system, where you are using lithium bromide refrigerant as a water. Here, a figure shows the lithium bromide vapor absorption system. In this system, the absorber and the evaporator are placed in a shell which operates at the same low pressure of the system. The generator and the condenser are placed in another shell which operates at the same high pressure of the system. The principle of operation of this system is discussed as, now see the figure of lithium bromide absorption refrigeration system. So here we are having an evaporator, here we are having a condenser and a generator. Here we are having a heat exchanger, and here we are having a cooling water. So that is a simple setup of lithium bromide absorption refrigeration system. Now see here. So from this heat exchanger, the strong lithium bromide solution is passing, and weak lithium bromide solution is going out from the heat exchanger and is going into the generator. Now the heat exchanger, whatever the strong lithium bromide solution is passing from the heat exchanger, and it is going into this cooling tower, right? It is going in the cooling tower, and the water which is present in the absorber is also present, is pumped with this cooling water through the pump into this chamber, and, and the cooling water is passed into this evaporator. Thereby the low temperature, high temperature chilled water tubes will present at that point. Thereby the cooling water is passing into this chamber and it is going into the condenser. So where the cool water is going out, and this generator makes the water heat at this point, and the water is going through the pressure reducing valve to this evaporator, and it is passing into this absorber to the again heat exchange. So this is a process happening in this lithium bromide absorption refrigeration system. Now see the description. The water for the air conditioning coils or process requirements is chilled as it is pumped through the chilled water tubes in the evaporator. So, the water is pumped into the chilled water tubes in this evaporator process. Okay. Since the pressure inside the evaporator is maintained very low, therefore the refrigerant water evaporates. The water vapors thus formed will be absorbed by the strong lithium bromide solution which is sprayed in the absorber. In absorbing the water vapor, the lithium bromide solution helps in maintaining very low pressure needed in the evaporator. This weak solution is pumped by the pump. Okay, the weak solution pumped by the pump to the generator, where it is heated up by using the storm or hot water in the heating coils. What it is they setting? The weak solution is pumped by the pump to the generator. So weak solution on the this weak solution is pumped by the generator, pumped by the pump. This weak generation. So here, this pump will pump the weak lithium bromide water to the heat exchanger, to which one? To the generator. Yes, is pumped to the generator. A portion of water is evaporated by the heat and solution now becomes very more strong. This strong solution this strong solution is passed through the heat exchanger and then sprayed to the absorber as discussed above. So a strong solution, what happens? This strong solution is passing into the heat exchanger and is sprayed into the absorber. The weak solution of lithium bromide from the absorber to the generator is also passed to the heat exchanger. This weak solution gets heat from the strong solution in the heat exchanger, thus reducing the quantity of heat, thus reducing the quantity of steam required to heat the weak solution of the generator. Now, the refrigerant water vapors formed in the generator due to the heating of solution are passed to the condenser where they are cooled and condensed by the cooling water flowing through the condenser water tubes. Okay, the refrigerant water vapors formed in the generator due to the heating of solution are passed to the condenser, whereas the cooled and condensed by cooling water flowing through the condenser water tubes. The cooling water for condensing is pumped from the cooling water pond to the tower. Now what happens here? This cooling water first enters the absorber where it takes away the heat of the condensation and dilution. Now the condensate from the condenser is applied to the evaporator to compensate the water vapor formed in the evaporator. Now the pressure reducing valves reduces the pressure of a condenser from the condenser pressure to evaporate the pressure. Now the cooled water from the evaporator is pumped and sprayed to the evaporator in order to cool the water for air conditioning flowing through the chilled tubes. This completes the cycle. So what is the last point? The cooled water from the evaporator is pumped and sprayed in the evaporator. So the cooled water which is coming, the cool water which is coming outside of the condenser. So the balanced water is going into this chamber and it is forced into this evaporator and it is sprayed in this cooling water system only, right? This completes the total one cycle. Okay, this completes the one cycle. Next. Now we'll see one problem based upon this cycle. Okay, this lithium bromide absorption system. This is a setup. This is the total information of this system. Very easy. Coming to the problems for this system. See the first one. The following data refers to the lithium bromide plus water absorption system, and generator temperature is equal to 80 degrees, condenser temperature is equal to absorber temperature is equals to 30 degrees, evaporator temperature is equal to 10 degrees, condensate temperature is equal to 25 degrees. Steam enters the generator heating coil at 120 degrees centigrade and leaves at 100 degrees centigrade at condensate. Now the concentration of liquid leaving the generator is 0.65 and the enthalpy is minus 75. The concentration of liquid leaving the absorber is 0.51 and the enthalpy is minus 170. The enthalpy of vapor leaving the generator is 2620 kg per kilojoules per kg. The flow rate through the evaporator is 0.4 kg per second. Now find what? Find the pressure in the generator, the condenser, the pressure in the evaporator, the pressure in the absorber in mm of mercury, and second one is the tonnage, third one is the heat rejection to the condenser and the absorber, fourth one is the COP, and fifth one is a relative COP. So these are the 5 parts to be find out. Next, coming to the solution, what is the given points? The Tg is equals to 80 degrees centigrade, that is 80 plus 273. Tc is equals to Ta, that is equal to 30 degrees centigrade, and Te is equals to 10 degrees centigrade, and T2 is equals to 25 degrees centigrade, Th is equals to 120 degrees centigrade, Tl is equals to 100 degrees centigrade, and x5 is equals to 0.65, and xh5 is equals to minus 75 kg per kilojoules per kg, x4 is equals to 0.51, h4 is equals to minus 170 kilojoules per kg, h1 is equals to 2620 kilojoules per kg. M1 is equals to M2 is equals to M3 is equals to 0.4 kgs. That's the information, that is 0.4. See here, the flow rate through the evaporator is 0.4 kg. Now the lithium bromide water absorption system may be represented as shown in the figure. So just draw the line diagram of this lithium bromide solution. Now what is the things you have to find? See here, from one generator it is passing into this condenser, right, from the generator. So we are keeping a heating coil for heating about this liquid, and from the generator it is passing into the condenser where the cooling water coils are located in the condenser. From the condenser it is passing into the evaporator where you are having low temperature coil unit and high temperature chilled water tubes. From this evaporator, the liquid is passing into this absorber, and at this point it is getting evaporated. Cooling coil, it is getting evaporated, and it is passing from the pump to this point, and it is passing into this generator. So what is the fifth point saying? From this generator the vapor is passing down and it is again going into absorber where it is forming some problem. Now according to the problem, so what is the first point you have to find? The pressure in the generator. The pressure in the generator, condenser, evaporator, absorber in mm of Hg head. Now from the steam tables of dry saturated steam corresponding to generator temperature 80 degrees, the Pg is equals to 0.4736 bar. That is equals to 0.4736 into 760 divided by 1.013, that is equal to 355.33 mm of Hg. Now corresponding to the condenser temperature of 30 degrees, pressure in the condenser, Pc is equals to 0.04242 bar, that is 0.042 into 760 by 1.03. Now see here, the Pg is given as 0.04736 bar. Now the corresponding temperature we got. Now corresponding evaporator temperature at 10 degrees centigrade, Pe is equals to 0.01227 bar into 760 divided by 1.013, that is equal to 9.22 Hg mm of Hg. Now corresponding to an absorber temperature of 30 degrees, the pressure in the absorber Pa is equals to 0.04242 bar is equals to 0.04242 into 760 divided by 1.013, that is equal to 31.82. Okay, now see here, PA is equals to 0.4242 bar, that is 0.4242 into 760 divided by 1.03, that is 31.82. Now the tonnage or cooling capacity. So from the steam tables, H2 is equal to 104.75, and the enthalpy of vapor leaving the evaporator is equals to H3. H3 is equals to 2519.9. Therefore, the cooling capacity or refrigerant effect QE is equals to M2 of H3 minus H2. That is equal to M2 is వచ్చేసి H3 minus H2, that is equal to 966 kilojoules. 966 divided by 3.5 is equals to 2.56 TR. 2.5 is 276 tonnage. Now, third one, heat rejection into the condenser. Heat rejection to the condenser and absorber. Therefore, the heat rejection to the condenser QC is equals to, the formula is the QC is equals to M2 of H1 minus H2. M2 of H1 minus H2. So substitute the value M2 already మనకు given లో 0.4 ఇచ్చారు. So 0.4 of H1 value minus H2 value. Therefore 1006 kilojoules per second. In order to find the heat rejected to the absorber, find the mass flow rate leaving the absorber and generator. Therefore, let M4 and M3, that is equal to mass. Consider the mass balance for absorber. M3 plus M5 is equals to M4. And considering the mass balance of lithium bromide solution, the absorber, M4x4 is equals to M5x5. M4x4 is equals to M5x5, or M4 by M5 is equal to M4 by M5 is equals to X5 by X4. So substituting the value M4 is equals to 1.2745 to M3. Therefore, M3 plus M4 M5 is equals to 1.2475. Yes. Now M3 plus M5, M4 and ఏంటి? We know that M3 plus M5. Therefore, M3 plus M5 is equals to 1.2745 M3. M5, sorry. Now, ఇది తీసుకురండి 0.2745 M5 is equals to M3. That is equal to 0.4. That is equal to M5 is equal to 0.4 divided by 0.2745. That is 1.45. Now, M4 value. M4 value is equal to M3 plus M5. So, substitute చేసినప్పుడు we'll get the value of M4. Now, considering the energy balance for the absorber, therefore, M3H3 is equals to M3H3 plus M5H5 plus M4H4 plus QA. So substituting directly 1.452 into minus 25. Okay, now substituting the values of M3, H3, M5, H5. So we are getting M4H4 into QA. Therefore, QA value in substitute చేసినప్పుడు QA is equals to 1214.36. Now, fourth point. The fourth point is find out the coefficient of performance heat transfer rate in a generator QG. Therefore, considering the energy of a balance, M1 Q1 is equals to either thing what you know. So therefore, the M1H1 plus M5HY is equals to M4H4 plus QG. So substituting directly the values, right? So QG is equals to 1254.4. Now we know that the COP is equals to QE by QG, that is 966 divided by 1254.4. Now the heat transfer QG is equals to QC plus QA minus QE. So next thing is relative coefficient of performance. We know that COP is equals to COP max. The formula is one of next session we can derive this formula. Okay, the COP is equals to TE by TC minus TE, TG minus TA minus G. Right? Now the COP is equals to TE value substitute చేయండి, TC value, TE value. TG value, TA value, TG value. So finally you're getting 2.004. Therefore the relative COP is equal to COP by COP max. 0.77 divided by 2.004, that is 0.384. So this is a problem what we have discussed for this uh, lithium bromide refrigeration absorption refrigeration system, right? So tomorrow's class will discuss about the comparison, advantages of vapor absorption refrigeration system over vapor compression system, and the coefficient of performance of ideal vapor absorption refrigeration system, and the problems related to absorption, right? So tomorrow we'll discuss these three topics and we'll enter into the other topic of the unit 4. So if you have any doubts still here, so that you can ask me within 4 or 5 classes we can complete the unit 5 also. Okay, sorry, unit 4 also. So in this unit 4, so you can by heart the ammonia hydrogen or uh, Electrolux or 3 fluid system or lithium bromide system. So you are having a theory, the relation, the problem, the working principle, problem, or you make it the working principle, right? So let's stop here. So in this class we have discussed about the lithium bromide absorption refrigeration system, the ammonia hydrogen absorption refrigeration system, and the problems associated to it. So in the tomorrow's class we are having the balanced topics, that is the calculation of coefficient of performance of absorption refrigeration system, the internal small parts, and the other type part B of the unit 4. Okay. Okay. So if you get any question in this ammonia hydrogen, first draw this figure minimum 2 or 3 times so that you can easily by heart the ammonia hydrogen refrigeration system, right? Ammonia hydrogen refrigeration system. Next you are having 3 fluid refrigeration system where you are having the 3 fluids such as ammonia, hydrogen, and water as a medium, right? So just by heart this figure so that it will be very useful for you in the exam point of view. Okay, this is a lithium bromide absorption refrigeration system. Okay, right. So with this we'll stop the class. We'll continue the class tomorrow at the same time, same place. So thanks for having your class. Have a good day.